All right, let's get going. Welcome to the International Geosynthetic Society's North American Chapter's 2021 webinar series. My name is John Allen, and I'm the North American Chapter President, and I'll be your host for today. First, a bit about the IGS North American Chapter. Our mission is to provide leadership in advancing geosynthetics education and research to attain their appropriate and widespread use as engineering materials. The leadership within this nonprofit organization are volunteers. We could not provide this content to you without the support of companies like Menard Group USA. The Menard Group USA is an international specialty ground improvement construction company and part of the Soletanche Bracetnet Group within the Vinci Company. Vinci is one of the world's largest construction and concession companies. Menard works nationally and internationally, providing ground improvement services. Menard's techniques include wick drains, earthquake drains, controlled modulus column, rigid inclusions, vibrostone columns, dynamic compaction, rapid impact compaction, and soil mixing. Typical projects include support of warehouses, buildings, material storage piles, processing areas, embankments, roadways, port facilities, storage tanks, containment structures, and platforms. The Menard Group USA is committed to continuing education and proud to be a contributor to IGS North America Chapter educational content. Today, we welcome one of my former professors, Dr. Jorge Zornberg. Dr. Zornberg is the Brunswick Abernathy Regents Professor at the University of Texas at Austin. He has over 30 years of experience in practice and research in geotechnical and geosynthetics engineering. His research focuses on transportation geotechnics, geosynthetics, unsaturated soils, expansive clays, and environmental geotechnics. He served as president of the International Geosynthetic Society. He has authored over 450 technical publications, written several books, chapters, and been awarded 3 patents. Professor Zornberg received numerous prestigious awards, including the Presidential Early Career Award for Scientists and Engineers, awarded by the President of the United States. The IGS recently established the Zornberg Lecture Award in recognition of his contributions to geosynthetics discipline. First, a little housekeeping. We're only able to address questions submitted in the Q&A box through Zoom. Do not submit questions or use the chat function during the presentation. Questions will be addressed at the end of the presentation, and should your question not be addressed, we can respond to you directly at a later time via email. On behalf of Menard USA, IGS North America, and our 220 plus attendees, we welcome Professor Zornberg. The floor is yours.
Thank you very much, John, for the kind introduction. Thank you to IGS North America for inviting me to put together this first webinar in 2021. I'm delighted to do so. I'm very impressed with the series of speakers that are lined up after this webinar, and I'm thankful to Menard for contributing to and supporting IGS North America. The topic of this webinar, of this presentation, is geosynthetics in roadway applications. This is a huge topic, and let me tell you, I'm going to tell you a little bit on the focus of this presentation. I know that in here we have many people that may be familiar with geosynthetics and not with roadway, so let me give you an ABC on paved roads, which is going to be the focus of this presentation. All we're doing is we're essentially creating we cannot define statics. So if we have a vertical load added to this surface course, this vertical load will make it to the subgrade. And our objective is to have a stiff multi-layer system so that we transfer the load that needs to make it to the subgrade, but in as wide of an area as possible. So that's why we're going to have typically a surface, an asphalt overlay. We're going to be dealing in this presentation with flexible pavements, with asphaltic layers. As a retrofitting, very often we have asphalt overlays. Then we have a comparatively expensive layer of granular material with strong free draining material. Then in some cases, we do have a lower quality granular material that we call a subbase, and eventually we make it to the subgrade, which is essentially where the road goes, and we have very little control on what the subgrade is going to be. All right, so how are geosynthetics gonna help in these roadway applications? And on that, I have some great news for you. Very, very good news. There is a huge number of geosynthetics with a wide range of properties that can be used in numerous roadway applications. This is to fulfill many different functions through a wide range, a wide variety of mechanisms. This is great. We have the opportunity to improve performance. We have the opportunity to reduce costs. This is a very competitive market which fosters innovation. This is wonderful. And there are opportunities to optimize solutions, not only to address cost and performance, but also aspects such as sustainability that are becoming increasingly relevant for designers. But also I have some bad news, not so good news. And I'm going to ask you to read it by yourself. Yes, this is also a good news, a blessing, and a curse. The not so good aspect of this is that we really need to recognize the differences. And this may be a daunting mission. We have many geosynthetics, we have many properties, we have many applications and many functions and many mechanisms. And this may lead to confusion. And we have the risk of writing the specification for the wrong application and the risk of getting lost and not recognizing the significant benefits that geosynthetics can offer to roadways. So so that is the main objective of this presentation. The main objective of this presentation is not to get deep into any one of the different applications that we're going to talk, but I'm really going to step back. I'm going to step back and I'm going to look at the universe of geosynthetic applications in roadways, and the focus is going to be to understand the applications and the mechanisms. I'm not going to focus that much on the type of geosynthetics, on the actual properties, on the actual functions. They are going to come together after we have identified the right application and the right mechanism that makes that application work. In some cases, I'm going to get into some advances. Ultimately, what we want are the properties, and I'm going to get into some advances in the properties for use of geosynthetics in roadways applications. Very briefly, just to relate to you what are the main geosynthetics that we're going to be talking about in these applications. This includes geopixels and many types of geopixels, geogrids and geocells. I'm strictly going to focus on geosynthetics that are used within the body of within the structural component of the roadway. So I'm going to leave aside things that have geosynthetics that can do a great job in erosion control, in surface water management. I'm not going to get into those. So this is again, the cross-section of our roadway. Where is that geosynthetics is going to help us? What functions? And I'm just going to list them to you. I'm not going to define them. So the different functions, and we're going to come back to these, are going to be, some of them are mechanical, separation. We just want to keep dissimilar materials, we want to keep them separate. And reinforcement, this is also mechanical a function. And essentially, we're dealing with comparatively large strains. We're developing tension in cases in which we want to avoid some form of failure, of collapse. Then I'm gonna call this stiffening. That is also a mechanical improvement, but here we're gonna develop tension, but the focus is gonna be, the objective is gonna be the control of the formations. Then we have hydraulic functions, and this includes the filtration. We want the water to get through, but the fines not to get through. We may have, as a strategy, barrier. I'm going to touch on that in at least some cases when we want water to be out, we want containment. And finally, we may have as a strategy the internal drainage within the roadway. All right, so we have talked about the different functions: separation, reinforcement, stiffening, filtration, barrier, drainage, protection. Protection I've just added it here. How are we going to relate this to the applications? Okay, and the applications, that's going to be the focus of this presentation. I'm going to focus on 6 of these applications. And the reason and the way that we're going to come to each one of these applications is because the owner, the Department of Transportation, the private developer, has some design objectives. I want to mitigate reflective cracks in my future overlay. And the functions, we know why we want the functions. We want the functions because they are the gateway to get the right specifications for the right properties. But ultimately, we want to go, and I'm going to put my pointer here. We want to go from the design objectives all the way to the properties, and there is a missing link. That missing link are the mechanisms, and we need that mechanism that is going to link the application that we're going to be dealing with the function that we need to satisfy that application. So again, the focus is going to be on applications, and I'm going to walk you through 6 applications. In here, I have it ordered 1 through 6, essentially from top to bottom. One, we're going to start with the mitigation of reflective cracking in structural asphalt overlays. Then we're going to get to the unbound aggregates, the base, the subbase, and we're going to talk about stabilization of unbound aggregate layers. Then we're going to get to the interface with the subgrade, and we're going to talk about reduction of layer mixing, intermixing, and we're going to talk about reduction of moisture into the structural layers. Then we're going to get to the subgrade, and we're specifically going to talk about stabilization of soft subgrades and mitigation of problems associated with the presence of shrink swell subgrades, expansive clays, or frost-susceptible soils. We could have organized this in a different way. So for example, we could say that in some cases, we're going to talk about mitigation to detrimental effects that are triggered not by traffic loads, but things that we have not designed, the reflective cracking in structural overlays or volumetric changes in the subgrade. We could talk about stabilization of the base or the subgrade in cases, essentially, we want to either enhance or not to allow the degradation of the important properties that allow the good performance against traffic loads, or we need to avoid or reduce problems associated with that are time dependent, like layer intermixing and the presence of moisture. And I do not want to get hung up on the terminology. This is a terminology that was selected here for internal consistency. It's perfectly fine if the terms that we use, for example, either stiffening or stabilization, we use it as a function or as an application. Independent of that, the important aspect here is the content, the material that we're discussing. To facilitate this, my good colleague and friend, Errol Tutumler, and I have developed this table. And essentially what we're going to do in this presentation is I'm going to walk you through this table. And if you want, you can even go ahead and download it. I gave a easy URL, then we're going to put a link in here. But if in the meantime you want to download it, it's a one-page table, https://utexas.box.com/v/geosynthetics in roadways. And essentially, in the initial portion of this table, we're going to have the different applications and the different objectives. And we're going to go one by one. What we mean by applications, essentially, what is the technology involving geosynthetics that is being considered to improve the roadway performance? The objective is going to be why the designer or the owner of the roadway is interested in a specific improvement of the roadway in which geosynthetics can be helpful. The mechanisms is key, is how is that the geosynthetic is going to help achieve the goals of that application. And finally is the functions. The functions is, we need this because they are the gateway. It's for which actions should the geosynthetic be specially fitted, and it's through, after proper identification of the functions, is that we're going to get to the properties. So let's do it. So we have 6 applications to cover. And in case you want it, here I'm going to give you once again the URL in case you want to download this table and sing along. And then let's go to the first application. This is a very important one. It's mitigation of asphalt reflective cracking. So essentially, the objective is to retard or eliminate refractive cracking into structural asphalt overlays that are triggered by the presence of existing cracks in the old surface. So here we have, for example, an example of a paved surface in need of retrofitting. A typical maintenance, large maintenance operation would be to place an asphaltic layer, perhaps 2, 3, 4 inches thick. The problem is that we may have flexural and shear modes that very quickly may lead to the reflection of the pre-existing cracks into the brand new asphalt overlay. Now, let me tell you upfront, this is a very reasonably complex application, and indeed we have 2 quite different strategies to address this problem using geosynthetics. One, I'm going to identify it as tension development. We're going to enhance the stress distribution within the asphalt overlay in the vicinity of the pre-existing cracks. If we are able to decrease the magnitude of the stress concentration, we're not going to trigger the crack, and that's the strategy in this particular application. There's a different one. That is stress relief. In stress relief, we're going to allow crack propagation, but we're going to force, or we're going to educate the crack to propagate in the right direction. Specifically, we're going to force the crack to develop along the interface between the new overlay and the pre-existing asphalt layer. So this is a view that essentially indicates the tension development strategy that I've just mentioned. You can see here the cross-section of a roadway. We have a pre-existing crack in the old pavement layer, and essentially what we want to avoid is that this crack reflects, for example, by shear and bending with its wheel loading into the new asphalt overlay. The idea in this case is that the the geosynthetic will allow the development of tension that will not necessarily avoid the crack to move, but will distribute the strains in a way that we do not reach the threshold that will lead to the triggering of the crack. A different strategy is a stress relief strategy. In this particular case, here we have again the pre-existing asphalt layer with the new asphalt overlay and a geosynthetic that is going to act as a stress relief mechanism. And in this case, the properties are going to be, we cannot ask reinforcement and stress relief. Is either one or the other. So, but in this case, rather than having the reflection of the crack without the geosynthetic, once we have the geosynthetic, that it will act as stress relief, essentially what we're forcing is we are forcing a differential of lateral displacements within the pre-existing asphaltic layer and the new asphalt overlay, and a crack will develop, but it will develop along the interface between the new overlay and the pre-existing asphaltic layer. So what are the geosynthetic functions? So we have identified the mechanisms, and that is my main goal in this webinar. Once we have identified the mechanisms, what are the functions? Well, if I want a tension development, I need a reinforcement. I need a geosynthetic that will develop tensile strength and stiffness as well. If I'm gonna go for stress relief, some could call stress relief even a different function. I'm gonna call it as being within the separation family sub-functions. But independent of what is either one or the other. We may have a third objective, but it's different than stress, than it will improve the performance in the road, but we can also have a different objective that I didn't talk about, which is having a barrier to moisture infiltration. In case we have the cracks developed, then the barrier will mitigate the continued infiltration into the additional into the layers. We can even have combinations of, for example, reinforcement and barrier, or stress relief and barrier. So I'm not going to dive into the details of the properties, but as you can imagine, once we have the functions, we can have a good sense of what the properties are going to be. Tensile strength, unconfined tensile stiffness, asphalt retention, survivability related properties. That's a common one that we're going to see over and over. I'm going to touch very, very briefly on the new one. Simply from time to time, in several of these applications, I'm going to cover at least one aspect that I consider that is a new direction or a new property in which that is being considered in the industry. And this is the post-peak. This is the residual shear strength of the asphalt geogrid composite. The benefits are essentially of this application is that we're going to maintain the integrity of the structural asphalt overlay. And if we maintain the integrity, we will ultimately avoid the water intrusion that will accelerate the degradation of the asphaltic layer. There are many different types of geosynthetics that are used in these interlayers. They are known with different names: geotextiles, glass geogrids, polymeric geogrids, geocomposite, hybrid geomats, and peel and stick interlayers. Many different types of geosynthetics. In the case of in which we're interested in the tension development, just as illustration of how the geosynthetics may work, this is in the monotonic loading, which is not the real loading. You can see a significant difference in the load that is needed, and actually in the mode of failure. This is a geosynthetic reinforced specimen. This is a control specimen. And what is interesting, in my opinion, is that the control specimen, once it fails, it fails. There is no residual contribution. But in the geosynthetic reinforced specimens, essentially once after we have reached the peak strength, we continue, the geosynthetic continue to help. So the energy continues to develop energy even after having reached a geosynthetic. This is for polymeric geogrids. After having reached what we know as peak, as failure. So there is a post-peak, a post-failure, a continued benefit of having the geosynthetic. This is on cyclic loading. I'm not going to get into the details, but similar, the results in specimens conducted under cyclic loading in shear are also consistent with the monotonic one. Different results, but similar, consistent trends. Here is, for example, here we have in the control specimen a very clear, well-defined failure. Here is failure, but is not a much more distributed area in which the failure occurs. Essentially, I'm showing you the results of cyclic loading under different amplitudes, and the green is the geosynthetic reinforcement load versus number of cycles, and the black is the control. And this is just to tell you that the improvement that the geosynthetic can provide in the asphaltic layer is significant. It can lead to a significant increase in the design life of the structural overlay. Let's go to a next application. So we started from the top asphaltic layers. Let's go to stabilization of unbound aggregate layers. The objective in this case is it has to do with stiffening the base or the subbase, so the unbound aggregate. And this is done by providing an initial increase in modulus. We're talking about modulus. And the other problem that we have is that the roads, after compaction, the base is born very stiff and very good. The problem is what happens with time. So avoiding the the time-dependent degradation of the modulus is a key additional benefit of this stabilization application. So the mechanisms by which this is going to occur are going to be essentially one. There has been a lot of discussion in the literature on what is the real. We know that it works. We didn't know for a long time, we know that this works. We didn't know why it works. And we have proposed a number of mechanisms. I think that there is consensus that the real mechanism, the most relevant mechanism is one. And it is developing lateral restraint through tension and shear transfer to minimize the tendency of the aggregate, of the unbound aggregate to displace. Let me show you this with a cartoon. So here we have a non-stabilized road base, and is subjected to the cyclic loading of the wheels. And what will happen with time is that there will be a tendency for the aggregate to displace. An aggregate is a wonderful material, but only if confined. If we have a clean aggregate and it's not under confining, this is a lousy material. So what may happen is that because of a lateral displacement, and the displacements are exaggerated, but this is the idea, we create a domino effect. Tiny lateral displacements may lead to decreasing the confinement of the aggregate. If we decrease the confinement on the aggregate, we lose the stiffness, the modulus in the aggregate. If we lose the modulus of the aggregate, we lead to a concentrated stress distribution that eventually leads to early failure by rutting. This is serviceability failure, very different than collapse, and very difficult to quantify and to design for. So the idea here is that the geosynthetic that will stabilize the base essentially will minimize or ideally prevent and impede that lateral displacement that will eventually lead to the loss in confinement and the degradation of the modulus. That is the mechanism by which the geosynthetic will contribute to this second application, stabilization of the unbound aggregate layers. What is the function that we need? The function that we need is one, and this is important, is only one, and that's going to be the function of stiffening. We need to develop tensile forces, but the tensile forces that we will need to develop are on the comparatively low strains. Consequently, it is the stiffness and not the tensile strength, the property that will govern the design and the performance of stabilized unbound aggregate layers. What are the properties? I'm not going to get into the details, but let me just list some of the properties that have been used. Unconfined tensile stiffness. We need developing stiffness, and we need transfer of the load between the sol and the geosynthetic. Let's call it tau sol geosynthetic. I'm going to tell you a little bit more about some combined properties that combine into a single property, both the stiffness and the load transfer mechanisms. Junction strength has also been specified and adopted in the case of geogrids. The benefits is that we are going to provide an increased modulus at the time of construction, an initial increase in modulus, but also an equally important, also an equally important is going to be the minimizing or eliminating the degradation as much as possible, the degradation, the time-dependent degradation of the modulus in the unbound layers. What are the approaches for design? I'm not going to get into the details of the approaches for design, but they exist. They are established in AASHTO, and they are established through procedures that require additional data to fit the benefits that we get when using geosynthetics to stabilize a base, for example, into the framework, for example, of AASHTO 93. This is, and the objectives have been, okay, for a given design life, let's reduce the thickness of my base, or for a given base thickness, let's extend the design life. These have been the objectives, the traditional design objectives. The approaches are TBR, BCR. They essentially quantify the improvement that in the number of cycles in the design life, for example, that the presence of the geosynthetic will add to a given cross-section of a roadway. I'm going to touch very quickly on the quantification of a new property, the stiffness of the soil geosynthetic composite. This new property, I didn't tell you, I just threw at you that the mechanism is lateral restraint, and this comes after long discussions and research over the years, in which other two mechanisms, membrane tension support and bearing capacity increase, have been essentially identified as potentially existing, but the level of displacements, the level of shear strain that are needed to mobilize those mechanisms leave us with one remaining mechanism, which is the lateral restraint, minimizing or eliminating the tendency of the aggregates to displace permanently, monothonically, due to the wheel loads. Without getting into the details, this testing, we can simulate this condition that is here in blue in the laboratory in order to obtain the confined stiffness of the soil geosynthetic composite under low displacements. I know that this is a mouthful, but think of what we want is a stiffness, what we're getting is a stiffness, but it's a confined stiffness. And it takes into account not only the innate stiffness of the geosynthetic, but also the ability to develop that stiffness through interaction with the soil. Let me show you something. We have done this test not only in this box here, the yellow box, but also in this transparent box. And the transparent box allows us to see the development and the straining and the twisting of the ribs, in this case of a geogrid. But the trick in here is that we need a transparent soil in order to observe this. And this is the front view, and we can even see the lateral. And in this case, we see the geosynthetic here is vertical, and we could see the development of the shear bands that ultimately this stiffened zone that we're after. Just to tease you on this, but this is another reason and the result of this stiffness of the soil geosynthetic composite comes after additional evaluation using transparent soil. And what is this transparent soil? Well, it's fused quartz, very pure quartz. So it's a granular material, but it turns out that if submerged into a liquid that has the same refractive index as the pure quartz, then this becomes transparent. And even more, it gives us even the ability to observe the particles in a given plane if we use laser technology. But independent of that, essentially what we ultimately can observe is the same soil geosynthetic interaction testing, but now we can observe the development of the strains and the load contribution of the different reefs as the test progresses. This has been implemented, this test has been implemented, is being implemented recently by Texot, and I'll be happy to share the information with those of you that may be interested. So we have covered now 2 of the 6 applications. Let me go to the third one, reduction of layer intermixing. The objective is comparatively simple, but very important, to avoid the contamination of unbound aggregate layers with fine-grained subgrade salt particles. This may lead to disaster, and this is an example of contamination of a good quality base with a soft soil. And this is the difference that can be observed when using a simple geosynthetic that acts as a separator between, in this case, the base and the subgrade. The mechanisms, there are two mechanisms that we want to avoid and minimize. Without the geosynthetic, we would have the loss of the unbound aggregate particles into the subgrade, and that's some sort of a local bearing capacity failure. But we will also have the pumping, upward pumping of the fine-grained soils in the subgrade into the aggregate. This is a cartoon to illustrate that. And here we have a road without a geosynthetic separator with a soft soil, high degree of saturation soil, and with the wheel loading, we will have the pumping, upward pumping of fines into the voids of the aggregate, and we would lose the particles of the base. Effectively, clay plus aggregate is clay. So a contaminated aggregate will behave much more like the subgrade material than as the original aggregate material. And the solution to this is very simple and very inexpensive, and is placing a geosynthetic separator in between, in this case, the base and the subgrade. So what are the functions? The functions is clearly separation, and because very often we're dealing with the presence of water, filtration. So what are the properties? Now that we have identified the functions, we can do the next step and get the properties. The properties, essentially, the main thing that we need to ask the geosynthetic is just exist, just be there. So essentially, if the geosynthetic survives, and there is a series of index properties, mechanical properties quantified into a specification AASHTO M288, if you survive, then you will do your job of being a separator. And we need additional, in this case, hydraulic and filtration properties, quantifying the permittivity that has to do with the hydraulic conductivity through the geotextile in the normal direction, and some measures of the particle of the pore size distribution, which we identified as the apparent opening size. Again, I'm not diving into the properties, just telling you that once we have properly identified the function, we can do the next step, which is coming up with the right properties. Benefits, we will continue to use the as design thickness of my base. That's a very expensive component of the roadway, and we design the thickness. If we decrease the thickness over time, that's a big problem, and we will maintain it just by having a separator. Or even if we will maintain the contamination, will also, of course, lead to a reduction in the quality of the unbound aggregate materials. All right, so we have gone through asphaltic layer, base, and reducing the intermixing. Something else that may happen, particularly at the interface with the subgrade, is another important application, another important problem for which we have an application, which is the reduction of moisture in the structural layers. And here we have a view of a roadway and the many different potential sources of moisture. Moisture in the structural layers is not good for the high modulus that we need that structural package to deliver. So the objective is to provide in-plane drainage to minimize the accumulation of moisture within those structural layers. What are the mechanisms by which geosynthetics can help us? We can identify at least two mechanisms. One, I'm going to call it conventional or gravity-driven lateral drainage. That is, essentially, we're going to develop drainage, but this drains, and this may be counterintuitive, but drains only drain free water. So once we have saturation, free water, our conventional gravity-driven drainage will take place. This will not allow the decrease of the moisture that is stored, for example, within a high moisture content, but not necessarily saturated subgrade. Then we have the enhanced or suction-driven lateral drainage. This is in-plane flow that occurs under unsaturated conditions. Non-woven geotextiles and woven geotextiles will do the job, for example, in gravity-driven lateral drainage. In this case, we need something else. We will need special yarns, and we're going to call this, or has been called, Wicking Geopixels. And in this case, the difference is that this will allow not only the drainage of free water, but also stealing moisture from the high moist from that may be accumulated and stored under unsaturated conditions in the base or in the subgrade. So the idea is that, again, here we have a cross section with multiple sources of water, sometimes coming from the top down, sometimes coming from the bottom up, capillarity. And the moisture leads to a decrease in the modulus, and this leads to failure by rutting of our roadway. And the idea is that by having in-plane drainage, we will have the ability to maintain the modulus both of the structural layers and of the subgrade. So what are the functions? We have identified the mechanisms. Now we need the functions, and the functions are going to be separation. We need to still maintain the separation that we talked in the previous application, but in this case, we also will need filtration. The water will need to reach the drain, and lateral drainage. The properties are going to be in cases that we have will depend on what type of mechanism we're tapping into for lateral drainage. This will include transmissivity, a measure of the in-plane hydraulic conductivity of the geosynthetic, or suction-driven flow capacity in the case of Wicking Geopixels. Permittivity, apparent opening size, and solvability related properties will also be relevant. So the benefit is that we're going to avoid or minimize two things. One, if we have a high degree of saturation in the subgrade, we may have even generation of positive pore water pressures that may lead to early failure. But in addition to that, we will also avoid or minimize the decrease in the modulus of the structural components of the road. So these are two important benefits. One way of quantifying how important it is if you look, for example, if you're familiar with AASHTO 93, there is a factor. A factor is that affects the structural capacity, the structural number, and affects the structural layer coefficient. This is it's related. This factor essentially penalizes the modulus, the structural number, depending of the percentage of time that we anticipate that our roadway will remain saturated. And this will depend on that percentage of time. How often is that we're going to have a high degree of saturation, and also the quality of the drainage. And this can be a penalty as 40% of the original modulus if we have poor drainage conditions, or even a benefit, an increased modulus if we can guarantee that we will remain under low degrees of saturation. This is an example of the use of non-woven geotextiles that provide separation, filter, and in-plane drainage of free water. This is even a geocomposite, and you may recognize a young Barry Christopher in that picture using a geocomposite with horizontal drainage layers. And the newcomer, which is enhanced lateral drainage using Wicking Geopixels. I'm not going to get into the details of the Wicking Geopixels. Let me just tell you that the trick is to allow drainage not in between the yarns, not within the yarns, but allow drainage within the actual fibers. Actually, the fibers have a high specific surface that promotes capillary action. So this would be this cross-sectional fibers under full saturation, let's say quantified by the transmissivity. But if we are under unsaturated conditions, then this drainage will continue. It will be small flow, small volumes, but continuous volumes under unsaturated conditions. And remember, the goal in here is not necessarily drain free water, is to steal moisture from the subgrade and structural layers. And this is an example of one such use in which is kind of obvious the presence of a geotextile, in this case with enhanced lateral drainage, and the impact that the presence of this geosynthetic has on the moisture content of the layers of the soil that is in contact with this geotextile. Okay, let's now go to subgrade stabilization. What is the objective? This is also stabilization, but what we want to maintain is we want to tackle in the subgrade. And what we want is to increase the bearing capacity of soft subgrade soils. There are two key mechanisms that have been identified. Both have to do with the increased bearing capacity in the subgrade soils. One, and probably the most relevant, is what is identified. I'm going to come back to this with a cartoon, the vertical restraint of the subgrade. And the other is going to be a membrane effect, essentially a load that develops once the geosynthetic deforms enough to have an out-of-plane component of the load. Let me show you these two mechanisms in a cartoon. So here we have a road that is a non-stabilized subgrade. And let's say that this is a very soft subgrade. And what we want to avoid, this is a potential failure surface that we call a general shear failure surface. What we want to avoid is that we mobilize shear, high shear into the subgrade to the point that we change the mode of failure into a punching type shear type. And this is essentially what we're trying to avoid by using geosynthetic to stabilize the subgrade. This is instead the impact that the presence of our geosynthetic placed at the interface between the subgrade, the soft subgrade, and the base may have. How is this geosynthetic how is that this will work? Well, this geosynthetic will develop tension. But notice that there is an out-of-plane component in this geosynthetic. The tension is developed along the plane of the geosynthetic, but in the central portion, we may consider that we have an out-of-plane component that will decrease the magnitude of the load that is applied, that comes from the wheel, and is applied directly to the subgrade. That's one benefit. But the most important benefit is that this geosynthetic, you can think of it as being hanging on the, not within the wheel path. We have the mechanism that we identify as membrane effect, but beyond the wheel path, we have another mechanism that is the subgrade restraint. We're pushing the restraint, the lateral, the subgrade downwards. We're restraining that subgrade. And if you remember the bearing capacity equation, we have this affects the Q component of our Terzaghi equation of bearing capacity. It's good to have surcharge right next to the main load that we're evaluating against a bearing capacity failure. All right, what are the functions? The functions are reinforcement and stiffening. We need tensile strength, we need stiffness. We're typically dealing with water, so we will also need filtration. I'm going to accelerate a little bit in here. Here are the list of the properties. We have identified the mechanisms. We can define the functions. We can define the properties. And the benefits, essentially, we're going to minimize the time-dependent rutting by minimizing the vertical and shear stresses in the subgrade, and by redistributing the loads in contact with the subgrade. Just to give you an example of how bad are the sites that we're referring to, this is a project in which geosynthetics were used to stabilize the subgrade. The strategy is to place a working platform, and essentially what the geosynthetic does, it allows to minimize, first, that the loading platform gets lost into the subgrade, and second, that the thickness of the subgrade of the loading platform is minimized. There are probably, this is the one application that has the best understood and best articulated design methods. This is an original one that I'm showing for simplicity. This is Giron array, in which we have a certain thickness here in red of the loading platform without geosynthetics, and that thickness gets reduced if we have geosynthetics. This methodology has been improved, and the state of the practice is the methodology by Giroux and Han that builds on this original one. And last one is the mitigation of distress induced by shrink swell subgrades. This is a road near my home here in Austin, Texas. This is Turnersville Road in Buda, south of Austin. And here we have these longitudinal cracks. These longitudinal cracks are not due to traffic loads. These are due to, sometimes we call them environmental loads. These are due to volumetric changes of the subgrade. So the objective on the use of geosynthetics in this type of projects is to retard or ideally eliminate the environmental longitudinal cracks that are induced by either expansive clays or equally important, frost-susceptible subgrade soils. The strategies are many. One is to maintain the integrity of the unbound aggregate layer to in turn minimize or impede the triggering of the longitudinal cracks. But there are other strategies, such as controlling the moisture distribution, that the fluctuations of moisture that occur within the subgrade. Another one is to maintain the integrity of the asphaltic layer to fight the development of longitudinal cracks by reinforcing the asphaltic layer, or finally by ultimately avoiding moisture fluctuations at large using barrier. I'm going to talk mainly about the first approach, the first strategy that has proven to be very successful in Texas. This one strategy, by maintaining the integrity of the unbound aggregates, essentially minimizes the concentration of stresses that triggers those longitudinal cracks. And ultimately, by providing lateral restraint, which we already talked about when we talked about stabilization of the unbound aggregates. But in that case, the goal was to maintain or increase the modulus of the unbound aggregates. And also, and very importantly, we're going to add ductility. By the presence of the geosynthetic, we're going to add ductility to the unbound aggregate that will now tolerate these movements. We're not fighting necessarily the development of these movements. We're fighting the problems associated with these movements. Let me show you a cartoon. So here we have a road without a geosynthetic on expansive clays. And during the wet season, it turns out that the shoulders will wet up much more and rapidly in comparison to the center line of the road. Then comes the dry season. And in this case, let's call it the drying front will advance also from the shoulders. But the changes will occur close to the shoulders and not necessarily during is close to the center line. This is what causes, this is a flexion problem. So we're going to have heave during the wet seasons, and we have measured this, and settlements during the dry seasons. And at the end of the dry seasons is when we have the development of the longitudinal cracks. It's a flexion problem. How do we address this? By using the strategy of maintaining the integrity of the unbound aggregates. This is done essentially by adding ductility and distributing the strains within the unbound aggregate. And this is essentially what we are doing. What are the functions? Because we're using this strategy, the function that we will need is stiffening. And in this case, we will need to maintain the stiffness and the ductility of the base. So these are the properties consistent with the ones that we discussed when talking about unbound aggregate stabilization. And the benefits are that we're going to maintain the integrity of the asphaltic layer. We're going to eliminate those longitudinal cracks and consequently eliminate as well the water intrusion. I'm going to go very quickly through an example in Texas. Texas is in bad shape, but the entire central US is in bad shape with the presence of expansive clays. Blue in this map, USGS map, and red is highly expansive. You're familiar with Texas. 4 of the 5 biggest cities in Texas are along this corridor of highly expansive clays: Fort Worth, Dallas, Austin, San Antonio. And seeing is believing. I'm not going to get into the details, but what you see here is 2 lanes, one with longitudinal cracks, one without, one stabilized with geosynthetics, the other not. So this is a good evidence that this works, which has been quantified. And in this case, what you see in this, for that particular road, is the measurement in the vertical axis of the performance, the percentage of longitudinal cracks versus time during a dry season, a particularly dry season. And what we see here, the increase in longitudinal cracks in not one, not two, but three different geosynthetics. And this is the case in the control section without geosynthetics. It's unambiguous that the use of geosynthetics protects and minimizes problems associated with the presence of expansive clays. And even more, in this particular project, there was also lime stabilized sections. And this dashed line is the increased vertical axis crack percentage, horizontal axis time, the increase in cracks of the time of the lime stabilized sections. The moral of this story is that lime may prevent the movement. That's the goal of the lime stabilization, but either you prevent it completely, because if you have some movement, not only you have movement, but you have a brittle surface that will trigger that crack. Summary. I've rushed you through many applications on geosynthetics in roadways that involve well-defined mechanisms and geosynthetic functions. There are significant opportunities for improving roadway performance by using geosynthetics in applications such as, and this is only a partial list: mitigation of reflective cracking in structural asphalt overlays, stabilization of unbound aggregate layers, reduction of layer intermixing, reduction of moisture in structural layers, stabilization of soft subgrades, and mitigation of distress induced by shrink swell subgrades. Very important is and that's the main objective of putting all together, stepping back and looking at all these applications at once. Identification of the mechanisms is key to identify what are the geosynthetic functions that we need. And the proper identification of the geosynthetic functions is in turn key to establish the properties that we need in the design and specification of the geosynthetics. And with that, I thank you so much for your attention.
Thank you, Professor Zornberg. During the course of the presentation, we've had a few questions come in. Now is the time to enter questions in the Q&A chat room in Zoom, and we'll take a second to address some of those. So first question is from Javier Gamero, and he's interested in MSE walls along highway projects and the use of PVA grids. And I'm not sure if this is a commercially oriented question or not, but thoughts on that, Dr. Zornberg?
Yeah, I didn't focus on walls in this particular case. So certainly, I believe that the question is related to geogrids, and geogrids can be used in many of the applications that I have identified. But this is with or without the presence of walls, so I may not understood that exactly the question.
Okay, well, we'll move on. Mr. Madani asks about strain, and I think the intent of his question is how much strain can be allowed, or what strain ranges are we working in before we start to see the failures and the development. What are we paying attention to there? And maybe how does that relate to the 4th generation test?
Okay, so I believe that this question relates to the mitigation of reflective cracking, and which is in asphalt overlays, even though cracks are also induced by movements in the subgrade. In this particular case, I cannot tell you exactly what is it, is because we're talking about highly concentrated deflections. If we have a given deflection that is caused by a pre-existing crack, if that deflection occurs over 1 millimeter or over 1 inch, that's going to be the main difference, and that's how essentially the goal is for a given displacement that is triggered by the by the presence of pre-existing cracks, we want to distribute that displacement when it makes it all the way to the overlay through the geosynthetic. We want that 1 millimeter to be distributed over 1 inch rather than over 1 millimeter. So 1 millimeter in 1 millimeter is 100% strain. 1 millimeter over 1 inch is a much lower strain. So I do not have, it will depend, the triggering crack is energy, and this will depend a lot on the actual mix that you have. But all I can tell you at this point that we're decreasing the magnitude of the strains in orders of magnitude by developing tension within the interlayers.
So that kind of transitions into a question I personally had. In your table, and I didn't catch it at the beginning, do you identify classes of soils that one should be wary of in causing mechanisms of failure? Can you link soil classes to certain mechanisms? Like you really need to pay attention when you have these types of soil classes.
Well, in this particular case, and that's when comes the importance of defining clearly the objective of why we want the geosynthetic. So if I'm concerned with a subgrade, maybe what I do need is not necessarily to take care of the reinforcement of the asphaltic layer. So essentially what, in this case, we have two types of subgrades. And these are two different applications in this list of 6. One, if we have soft, low bearing capacity soils, that's a problem. And we need higher bearing capacity, and geosynthetics can provide that. And we have specific applications, specific functions that will address that. The second one is when we have expansive clays, for example. This is also clays, but actually the clays are always bad. But if they are soft clays, chances are that during the wet season, you have shear problems, bearing capacity problems. And during the dry season, you have movements or changes in fluctuation in volumes, and that is also a trigger for a different type of, for cracks, different than the ones that we discussed for the asphalt overlay. In this case, these are cracks that are due to the flexion of the entire structural package because the shoulders settle in relation to the center line of the road. So yes, two specific types of subgrades then that geosynthetic can address are, one, subgrades in which you have low bearing capacity, and there's a big collection of subgrades that fall under that category, and that depends also on the degree of saturation. And second, subgrades in which you are concerned with volumetric changes, expansive clays and frost susceptible soils.
Okay. Jaime Castro asks, is there any experience of geosynthetics controlling the washboard effect that happened on unpaved roads, say in rural Australia, Africa, or South America? And I got to say, Jaime, that we have washboard roads here in North America as well, and plenty of them. But would you like to
control what? Maybe I couldn't understand. I couldn't hear you correctly.
Washboarding on unpaved roads. How would you address that with geosynthetics?
I didn't touch on that.
I can give you an out, Jorge.
Go ahead, please.
We have Professor Jihan, presenting in about a month's time on geosynthetics and unpaved roads. And we
Perfect. I have the way out, but no, but that's a very, very good point. I am not aware, but I think that Professor Han will address soft subgrades, but I'll get back to this question. I'm going to research on this and get back.
Okay. I usually see it occur on rural roads, on steep inclines, and it's usually a result of two-wheel drive vehicles. And you get like a washboard effect, essentially.
Yeah. We're not driving on the geosynthetic, so need to think about that. Yeah.
Oh boy, the questions are coming in now. Let's get a few more. You're in hot water with Professor Holtz. He wants your reference.
Oh
no. And then maybe this one's subject for another webinar coming up. It looks like Fabio Fonte from Rio de Janeiro is interested in how this applies to subgrades for railroads. And I suspect it's similar.
Yeah. So again, can you repeat?
How is the application of geosynthetics in the railroad subgrade?
Okay, so that's a very good question. And a lot of what I presented, even though I've been talking about roadways, applies to railways and applies to airfields. So a lot. So here we call it base, in railways they call it ballast. But a lot of the problems that are addressed by using geosynthetics in roadway applications are also relevant for railways and also relevant for airfields. And even though the design methods, the core design methods that we have, that industry has to design roadways and airfields and railways are different, the problems are similar: bearing capacity, contamination, need for drainage, problems with expensive clays. They are all, probably the only one that I cannot count, the ones that I listed 6 applications. The only one that I wouldn't count as relevant for railways is mitigation of reflective cracks, because railways do not have a asphaltic layer. Other than that, all the other applications are relevant.
Excellent. So we can transition it very easily. Aman from Iran would like to talk, just to go briefly into the economics of this in optimization. And to piggyback on that question, can we use stronger materials in the lanes and weaker materials, weaker, cheaper materials on the boundaries?
This is an astounding yes. We can. The solutions using geosynthetics in roadways will lead to, for example, in a stabilization of unbound aggregates, thinner aggregates, thinner layers of aggregates. This translates also on sustainability benefits, because if you do not need to transport gravel to or aggregate from and mine the aggregate and place it, instead you save a couple of inches of base layer. This is an enormous economic benefit. The same goes for asphalt overlays. If we extend double the design life of the asphalt overlays, this has enormous economic benefits. So we can go one by one. If we maintain the thickness of the base layer over the design life of the roadway by eliminating the contamination of the base, we're extending the design life enormously. So all of these they need to be evaluated, they need to be designed. We need to understand and what are the proper mechanisms and the right properties, but they all will lead to good performance and almost always to cost-effective solutions.
Okay.